Hi, we've just gone through a series of videos that describe the components of our universe, and now it's time to propose a new idea of how they got here. Now, to do this, it'll be useful to be able to imagine our universe in 4 spatial dimensions. Well, unfortunately, since we're only 3-dimensional creatures, it won't be easy for us to do this. So I'm going to borrow an approach that was used by Edwin Abbott in his book called Flatland, in which he tries to explain the 3rd dimension to a 2-dimensional fellow living in a flat 2-dimensional world. So imagine that there's a 2-dimensional cosmologist who lives in a universe very like ours, but it only has 2 dimensions. Now, it appears to him that his universe looks like a flat disk, and his vantage point is at the very center. Now, of course, he realizes that observers located at any other point would seem to be at the center relative to their positions, and this is called the cosmological principle. That is, there's no special place or vantage point in the universe. Now, as he looks out, he sees that at very large scales, the universe seems to have the same contents and density pretty much everywhere he looks. Now, in scientific terms, his universe, like ours, is homogeneous. Moreover, it looks the same in any direction. And the name for this is isotropic. He notices that once out of his own neighborhood, the galaxies are all receding, and their velocity of recession is proportional to their distance. And this shows that his universe seems to be expanding. And when he runs the movie backwards, he concludes that at one time in the past, everything must have emerged all at once from a single point. Well, with tongue-in-cheek, he calls this event the Big Bang. Everything our 2-dimensional friend can observe is seen by sensing electromagnetic waves in various wavelengths. Some are visible, some not. And through experiment, he figures out that all of these waves move at a constant velocity, and that nothing in the universe can move faster. This speed limit implies that there's a maximum distance that light could have traveled since the Big Bang, and anything further away would be outside of his observable universe. The computation of this distance is complicated by the fact that the universe is expanding, and the actual light path would be more complex than we've shown here, but the result is that his universe appears to be a flat disk bounded by a circle that is almost perfectly round, with only minor deviations of temperature left over from slight variations in the original Big Bang explosion. Now, some of the 2D cosmologists have suggested that the 2D space they live in could have curvature and in fact could be curved back on itself so it was part of a 3-dimensional sphere. So instead of a flat plane, they could be living on the 2D surface of that sphere, in a disk that has a finite area bounded by a circle that lies at the farthest distance that light could have traveled since the Big Bang. Now, the universe they see appears flat, or nearly so, but this could be because they only occupy a small part of the surface of a much larger sphere. Well, our cosmologists can follow the math all right, but when it comes to visualizing a 3rd dimension, he just can't do it. So now we return to our 3D world, and we learn that we live on a 4-dimensional hypersphere bounded by a 3-dimensional spherical volume. And our small part of that hypersphere will have a small positive curvature, but appear to us to be as nearly flat space. Try to visualize what that looks like. And we can have some sympathy for the plight of our 2D friend trying to visualize the 3rd dimension. Now, we live in a homogeneous isotropic universe of nearly flat space, bounded by a 3D sphere that we perceive as the cosmic microwave background. We can't visualize the whole universe beyond the observable part that we can see, but the models we've developed concerning the behavior of the matter and energy and space we live in can certainly produce theories about the history and the future of our universe that are consistent with what we observe. Now, there's been many such theories over time. A while back, it was proposed that we lived on a flat disk balanced on the backs of elephants standing on a turtle. Well, fortunately, we've developed much better models through the works of Ptolemy and Copernicus, Tycho Brahe, Kepler, Newton, Einstein, Hubble, and other giants of astronomy. There are literally hundreds of these models today, and perhaps most of them are quite preposterous. But there is one, however, that represents the mainstream of cosmological science, and we'll describe it briefly. By and large, it presents a reasonable picture of how our universe has evolved, but there are a few areas that provoke unanswered questions. Now, in this video series, I'll attempt to fill in these areas with the ideas of black marble theory and bright energy. It may just turn out that the answers are much more simple than we thought. So, let's start by looking at the most widely accepted theory of the evolution of the universe. It's called the benchmark model. It begins a tiny fraction of a second, like 10 to the minus 43 seconds, after time zero. That's the time of the Big Bang itself. Now, before this time, current science has no idea what was going on. It's often called a time when the laws of physics did not apply. A common assumption is that all of the matter and energy that would comprise our universe appeared all at once from a point source or a singularity and formed a primeval fireball of immense temperature. By the time the benchmark model begins, the fireball has cooled to about a nonillion degrees, which is about 10 to the 32nd degrees Kelvin. All of the known fundamental forces are united into one, and the fireball consists of pure energy. And from this point, the benchmark model takes over and traces the formation of the universe as it expands and cools. Now, the model faces the task of taking this purely symmetrical object with no discernible features and producing, 14 billion years later, the complex universe that we see today. Well, a problem arises, however, because the physical laws that we know won't produce a universe with the internal structure, the flat curvature, the consistent temperature, and the cosmic microwave background that we've ended up with. I won't go into the details of these problems or why they should come up at all, but the problems were addressed in the 1980s by a theory called inflation. Now, this theory is usually included in the benchmark model. And greatly simplified, it goes like this. After the embryonic universe, with all its matter and energy had appeared as a minute ball of energy, the ball suddenly grew in size in a small fraction of a second. I mean a millionth of a trillionth of a trillionth of a second. And this growth period, called the inflation period, was mind-boggling. In the almost instantaneous time that lasted from 10 to the minus 33 to 10 to the minus 32 seconds after the Big Bang, the size of the new universe grew by a factor of 10 to the 26th. That's 10 followed by 26 zeros. Well, some critics have objected that this couldn't have happened because the velocity of the expansion would exceed the speed of light. But this is not a problem because it was the space itself that grew. Remember, we said to keep in mind that energy expands space. And this event was surely the ultimate example, and there's no limit on how fast space can expand. Now, at the end of the inflation period, we were left with a fireball of energy plasma that had cooled to a temperature of about a quadrillion degrees Kelvin, which was cool enough for the fundamental forces to separate and the processes of forming the elements of ordinary matter to begin. The expansion rate at that time was much greater than we see now, but it had slowed to a much more reasonable pace. Now, as cooling continued, the fundamental subatomic particles of ordinary matter began to appear and interact, forming quarks, and then protons and neutrons, and then atoms, and then molecules of hydrogen. And this provided the raw material to create stars and galaxies. Now, inflation theory proposes that small random quantum fluctuations occurred during the inflation that are magnified by later expansion into the structures that we see today, the walls and voids and filaments that form the clusters and superclusters of galaxies. Now, from this point on, the evolution of the universe is well established. The energy levels at that time can be reached today in the Large Hadron Collider, so many of the processes can be directly studied. So inflation can explain much of what we see, but there are still a few open questions. Now, there's no physical process that we know of that could cause inflation, and the many explanations offered are just pure speculation. We don't know how quantum mechanics operated during the inflation period to cause the fluctuations that resulted in the structure we see today. And it doesn't tell us where dark matter and dark energy come from. In the rest of this video, I'm going to propose an alternative to inflation provided by black marble theory. And the challenge will be to present a process that will end in the same condition that's predicted by inflation theory. So we'll need a hot, expanding fireball of energy that contains the material for the matter that will inhabit the universe, the density variations that will result in the structures that we see in galaxy clusters, and it would be useful to include a large dose of dark matter. So let's see how we get there. I'm going to start long before our Big Bang in a place that has at least 4 physical dimensions, possibly many more. Many cosmologists suggest that our universe came from what they call nothing, but I call this place the nihilo. It comes from the Latin phrase creato ex nihilo, or creation from nothing. The nihilo is populated by a large amount of black matter that is accreted into black marbles. We're especially interested in one of them that's grown to an immense size. It contains enough matter to account for everything in our universe. If we only account for what we see in our observable universe, it would be about the size of the Virgo cluster. But since that's only a part of the whole universe, it's probably much larger. This is the black marble that will explode and cause the Big Bang that will produce our universe. So, what will cause it to explode? Well, there are a few possibilities, but let's propose a likely one. Over time, the black marble has grown by accreting black matter from the nihilo environment. Eventually, something occurs to destabilize the black matter, and it begins to change its state to E energy. The event may start itself spontaneously, or it may be due to some minor disturbance in the marble itself. But the moment that this happens is time zero of the Big Bang. The small ignition event begins to progress rapidly through the marble, and the Big Bang is underway. Now, explosive physical processes that we're familiar with begin to take over. As matter is converted to energy, space is created, and the pressure begins to detonate the marble. The explosion resembles a nuclear reaction similar to those we see on Earth, though it probably proceeds through the matter at a faster rate since the black matter is more tightly packed than the nuclear fuel that we use. However, it's nowhere near the velocity proposed in the inflation theory. Although the expansion is slower, however, it explains the same problems that inflation theory seeks to solve. So let's pause a moment to make an important point. When we think about explosive formations that we're familiar with, we think of them as expanding into the surrounding space that already exists. Well, that's not what's happening in our universe here. The Big Bang explosion is expanding into the space that has been created by its own energy. We're observing the structure of the matter formation within our expanding three-dimensional sphere that's our neighborhood of the much larger four-dimensional sphere created in the Big Bang. Now, as the expansion and the detonation of the Big Bang proceeds, the temperature drops and the material needed to sustain the explosion is dissipated. In a short time, the explosion peters out. Its kinetic energy has been transferred to the debris of the original black marble, and the transition to the expansion phase of the new universe is underway. So, during the explosion, most of the matter in the marble that was not converted to energy was blown into a fine dust of black matter, made up of minute entities I call smithereens for obvious reasons. Now, as the temperature and energy fell from the extremely high levels of the explosion phase to the lower values of the expansion phase, a small percentage of the smithereens were affected. As the energy drops, it reaches a critical value that marks the crucial moment in the history of the universe. It's the moment of the creation of ordinary matter. Before this moment, the new universe consisted of an exploding fireball of energy at an unimaginable high temperature. The black marble was beginning to blow apart, but at the center, nothing existed but pure energy and exploding black matter. As the fireball expanded and the temperature dropped, the amazing process occurred that created all of the ordinary matter our universe will ever possess. Let's pause a moment to consider what we've just said. Inflation theory suggests that ordinary matter particles begin to appear spontaneously as the universe temperature drops right after inflation is complete. But black marble theory proposes a process for the creation of ordinary matter. Of course, it's pure speculation, but at least it avoids the idea of particles forming with no known cause. Let's discuss how that process might work. When we focus on the explosion phase, when black matter is being converted directly to pure E energy, there doesn't seem to be a possibility for formation of particles of ordinary matter. And likewise, there's no known process for creating new ordinary matter once the expansion phase that we live in today has begun. Yet, once the expansion phase is underway, ordinary matter comprises 5% of the residue of the explosion. So we're driven to the conclusion that it had to have been created during the short transition phase as the explosion energy fell and the expansion energy took over. There was no mechanism for ordinary matter particle production either before or after this moment. So all the ordinary matter our universe will ever have was created during this tiny period, during the first second of our history. Black marble theory proposes that there was a steady drop of the energy level as the explosion petered out. At the same time, there was a rich supply of black matter in the form of nearly infinitesimal smithereens of all sizes. The proposal is that the falling energy reached a critical level and resonated with a small percentage of the smithereens to set them vibrating. Now, these vibrating smithereens became particles of ordinary matter. The vibrations of the smithereens affected the new space that had been created in the explosion. Each particle created a field of waves like ripples from a stone dropped into a pond. Each type of particle created its own field, and the fields from different particles interacted with the others to permeate the new space with a seething content of energy. Quantum scientists call this the vacuum energy. It created an extremely complex environment of energy, space, and ordinary matter particles. During the last century, scientists learned to deal with it with the theory of quantum mechanics. And this theory must deal with many variables. Because the waves caused by particle vibration assume specific wavelengths associated with their energy can only assume discrete values. Particle movement in the resulting complex field can only be approximated by the probabilities of wave mechanics. The behavior of individual ordinary matter particles is often mysterious and counterintuitive. Nevertheless, the understanding of our universe provided by quantum theories is one of the crowning achievements of human science. However, let's make one point very clear here. According to black marble theory, quantum behavior applies only to the 5% of the universe we call ordinary matter. Black matter, the substance which makes up the part of the universe we call dark matter, is inert. It's a single amorphous substance that's not constructed of more fundamental particles. It doesn't vibrate, or it doesn't affect the space around it or other nearby particles. It's only interacting through gravity. And as we'll see later, it's only interacting with ordinary matter through the gravity of those small vibrating smithereens that create the particles themselves. Now, let's continue with the history of the universe. As the explosion dies out, the transition process occurs and the expansion phase begins. 5% of the smithereens now comprise the ordinary matter particles that we have in the universe. The rest of the smithereens are not affected, and the dust they created is blown into the new space created by the energy released in the detonation, and it forms the familiar clouds of an explosive formation. And the explosive process of the Big Bang in the original marble will cause it to create the walls and voids and filaments we see in typical explosions. As the universe expands, these formations will grow and form the structures that we see in today's universe. At the largest scale, the new universe takes the form of a very smooth sphere whose original explosive formation has been stretched and flattened by expansion. We've often seen fireworks displays where the explosive material has been very carefully packed into a spherical shape, and when it explodes, it fills the sky with a spherical shower of sparks with only slight variations. The black marble is packed very evenly, and when it explodes, it produces an almost perfect sphere with only small variations due to the explosive process. And this is what we see when we look at the cosmic microwave background. There's a lot of temperature variations, but they're only about 1 part in 100,000. So In both the inflation scenario and black marble theory, the universe emerged from the theoretical period before it became transparent and evolved into the structure we see today. But the two theories took very different paths to get there. From that point on, however, the benchmark model takes over and describes the development of the universe from there to the moment t sub 0. Well, that's what cosmologists call the present moment. So t sub 0 is right now. The explosion left a fireball of plasma that was expanding and cooling. According to the benchmark model, any antimatter was annihilated, leaving us with a universe containing just ordinary matter. There was a preponderance of black dust, but as the plasma cooled, the ordinary matter created during transition began to form protons and neutrons and electrons. But the temperature was still so high that the fireball remained in the form of an energetic soup of subatomic particles. Photons couldn't escape from this soup, so the universe remained in an opaque fog. In about 300,000 years, however, it expanded and cooled enough to allow the particles to form into atoms of hydrogen. And this allowed the photons to radiate out into the new space, and the universe became transparent. Of course, the ordinary matter had not yet begun to form stars, and so we call this period the dark age of the universe. Soon, however, the dense clouds of hydrogen began to coalesce and ignite into stars, and we were well on our way to becoming the beautiful place we live in today. So, there's the black marble theory scenario of how we got here. We were able to cover the time from long before the Big Bang right through time zero to the present without needing any new physics or peculiar processes outside of what we already know. Well, there's still a lot we don't know, however, and there are many mysteries about what goes on in the universe still remaining. And in the next section, we'll discuss what black marble theory has to say about them, especially that bane of modern cosmology, dark matter.